We're going to be moving on to a unit on electricity, and as I said yesterday, a lot of what we did earlier this year, I don't want to say you can forget about it, but we're not going to be using it nearly as much, almost like a clean break. And some of what we're going to be doing here today is going to be a review of things that you learned in chemistry. So for some of you, you're going to know it really well, others maybe not so well. Good idea for us to go through it either way. We're going to be spending some time today talking about electrical forces. And specifically, we're talking about electrical forces between static charges. Now, what does the word static mean? Now, if I say static electricity, what comes to mind? When you think of static electricity, you think of maybe getting shocked, right? But the word static doesn't mean get shocked. The word static, what did that mean in mechanics? Not moving. And we're talking about electrostatics, or static electricity. We're talking about charged particles that are stationary. Right, that's all it is. And then later this week, or maybe next week, we're going to start looking at what happens when charged particles start to move. But for right now, just static charge, stationary charge. And as we talk about electrical forces, you need to understand that physicists actually talk about 4 fundamental forces in nature. Every force that exists is one of these 4 fundamental forces. You ever heard that term before? The fact that there are 4 fundamental forces. We'll get to the demo in just a minute, but any guesses what the 4 fundamental forces are? Or anybody think they know what any of them would be? Give you a hint, we talked about one of these fundamental forces back in January. That helps at all. Now nobody wants to answer because they know they're going to be on. Go ahead, Mike. Yeah, gravity is one of the 4 fundamental forces in nature. A second fundamental force is the one we're talking about today. Electrical forces, actually electromagnetic forces, are the second of the 4. And the other 2 we don't talk about at all in this course. We do in AP Physics 2. The other 2 have to do with nuclear forces. All right, there's a nuclear strong force and a nuclear weak force. So all forces in nature are one of those 4, either gravity, electromagnetism, or nuclear forces. Now for electrical forces, just to demonstrate some things that you've probably tried before, let me go to the camera view here and Shift tab, one of those tabs. All right, I'll just back out of that. The camera view, here we go. So everybody can see this. You've probably all done this before. You've taken a balloon, maybe rubbed it against your head. And after you rub it against your head, you know it has some interesting properties. One of the properties is you can take the balloon and you could use it to pick up small bits of different things, like these pieces of styrofoam here. And obviously there's some kind of a force that's holding these things to the balloon. Even if I try to pluck them off, they just get pulled right back to the balloon. Right? So that's an example of an electrical force. Or maybe something else you've done with electrical forces before is if you take that same balloon and rub it against your head, you can go to a doorway and get the balloon to stick to the doorway like that, without using any adhesives or anything. There was a Physics Olympics event, maybe some of you participated in this, where you had to take 12 balloons and charge them and stick them to your body in the smallest amount of time. So there's some kind of electrical force at work there that causes that to happen. So that's what we're talking about here. And unlike gravity, that only ever pulls things together, if you think about gravitational forces, anything that has mass, they pull together. Unlike that, electrical forces can either be attractive or repulsive. In other words, they can pull things together or they can push things apart. Gravity never does that. At least if it does, we've never found it to do that yet. We've never found any 2 masses in the universe that get pushed apart because of a gravitational force. Instead, we always find that they get attracted together. But electrical forces can do either. And I want to demonstrate that. That's what it is, Alt-Tab. Using some Scotch tape. Get the camera over here in the right area. Have some Scotch tape here. I'm going to take off 2 pieces of tape, tear them off. And I'm going to take one piece of tape, place it right on top of the other piece of tape. In other words, stick them together. And then I'm going to quickly rip them apart like that. Now I want you to watch what happens if I take the two pieces of tape and get them anywhere near each other. See that? They're attracting each other. So there we're demonstrating the attractive force of gravity, and I have no idea whether that's going to show up on the recording or not. We'll find out later. And now I'm going to take the one piece of tape and put it down for now on the table and do the same thing again to another piece of tape. And now I'll take the original piece of tape, get rid of that, and take the one that I attached to the table and hold it near the one that just came off of there, and watch what these guys do. They attracting each other? Yeah, this is the repulsive nature of the forces. And that's something I'd like you to think about. Why in one case is there attraction? If I go back to this piece of tape, these two guys attract, whereas the other two pieces of tape repel. Right? But that does show you that electrical forces can be either way. Gravitational forces act on anything that has mass. Right? The reason this golf ball falls to the earth is because it has mass. The earth has mass. They pull on each other. What property does something have to have in order for an electrical force? What is it that I gave the balloon when I rubbed it against my head? Or what is it that I gave the tape when I pulled the two pieces of tape apart? Right, Taylor? Yeah, charge. Electrical forces act on anything that has a property of charge. By the way, which force appears to be stronger, electrical or gravitational? Based upon the demonstrations you saw. Electrical. Yeah, this balloon, teeny tiny balloon, pulled a piece of styrofoam upward towards it with an electrical force that evidently was stronger than the gravitational force that the entire Earth exerted on the styrofoam trying to pull it down. Right? Now you think about it, all I'm doing is taking a teeny tiny balloon, rubbing it against my head, and that's enough to overcome the gravitational force trying to pull that thing in the other direction. Electrical forces are much stronger than gravitational. Well, next question is this. If electrical forces are so strong and they depend on charge, where does charge come from? Where do we find charge? What's the source of positive and negative charge? Right, Anna? Yeah, inside every atom there's electrons that are negatively charged, and there's also what else? There's also protons that are positively charged. So the source of all charge is the atom. Every single atom has charged particles in it. This is a little chemistry review. Remember, in the nucleus, you're going to find protons that are positively charged, and you're going to find some neutrons that are neutral. We really don't care about them for purpose of this discussion. Where do you find the electrons? Right? Yeah, they're circling the nucleus, and they're really not orbiting like planets orbit the sun, but they're in a, we call it a probability cloud. But they're out there somewhere. They're away from the nucleus. There's a lot of empty space in between the two. You know, we say that they're in orbits, but we don't really think of it as being a planetary orbit, that type of thing. But they're negatively charged. So here's the next question. If every atom has charge in it, then why don't we see electrical forces acting on everything all the time? In other words, why did I have to rub the balloon against my head to get it to do anything? The balloon has atoms in it. The door has atoms in it. Why aren't those electrons and protons either attracting or repelling?
Because atoms usually like to make sure the charge is neutral by getting enough electrons to counter offset the photons they have.
Yeah, most atoms and bodies are electrically neutral. Most atoms are neutral for that reason. Most objects are neutral. And Mike, you hit upon the reason. You said most things are electrically neutral because inside every atom, let's take carbon for instance, right? Carbon has atomic number 6. That means there's 6 protons. But how many electrons would you find in a neutral carbon atom? You find 6. Remember that? The number of protons, the number of electrons, they're always the same as long as the atom's neutral. Most atoms are neutral. In other words, they have equal numbers of electrons and protons. And you may or may not know this is why we're reviewing it, but the charge of an electron is exactly the same as the charge of a proton. It's just that one's positive and the other one's negative. Right, exactly the same magnitude of charge, just different signs. And we call the charge of an electron E. So electron charge would be minus that value. Proton charge would be plus that value. So if you have equal numbers of them, when you add it all up, the net charge is going to be 0. So let's take another quick example of that. Let's say we look at a helium atom. Right? Helium atom. Here's the helium nucleus. In fact, let me full screen this to make it easier to see. Helium nucleus, and helium, you may or may not know, atomic number is 2. So inside the nucleus, there are 2 protons, and there are a couple neutrons in there too. We really don't care about them so much. So the total charge of the nucleus would be a charge of plus 2e. Each proton has a charge that we call E. There are 2 of them. And then surrounding the nucleus, a whole bunch of empty space, but then out there somewhere, you have a couple electrons. There are 2 of them, again, in neutral helium. Total charge of minus 2e. So you add it together, you get a net charge of 0. True for any neutral atom. By the way, any guesses what E stands for? I used to think it stood for electron. I was wrong. E actually stands for something called the elementary charge. Now what it's equal to is 1.60 times 10 to the negative 19th. The units are called coulombs. 1.6 times 10 to the negative 19th coulombs. We use a capital C to represent coulombs. And that's named after a guy by that last name who did a lot of the early work in establishing these electrical laws. So the elementary charge, which is the charge of the electron and the proton, is a very, very small fraction of a coulomb. But the reason it's called the elementary charge is because it's the smallest amount of charge that you will ever find in nature. You'll never find a charge less than E. And because of that, charge only comes in whole number increments of E. A monetary example would be, in the United States, the cent. Right? You never find any quantity of money less than a cent anywhere, do you? Less than a penny? And anytime you pay a bill, it has to be in increments of cents. You know, you never go to the department store and see something that costs $1.87.6, right?
Gas station.
Gas stations, they do that. That's right. You know, $3.43.9, right? But still, when you pay the bill, they don't ask you to pay for 0.6 of a cent or 0.7 of a cent. You still pay it in increments of pennies. So just to make sure that you understand what we're saying here. In nature, you could find something that has a charge of 3e. You could find something that has a charge of 5e. You could find something that has a charge of 100e. All those are possibilities, but you will never find a charge of 2.67e. Right? It does not exist. Right? Charge comes in increments of that elementary value. Any questions so far? We'll get into this. Well, how does something acquire a net charge then? Now, if we start out with atoms being neutral, equal numbers of protons and electrons, how does something acquire a charge? What was it that I was doing when I was rubbing the balloon against my head? Right, Anna? Yep, I was transferring electrons from one object to another object. Now understand that coulomb that we talked about a minute ago, we said that one electron is a very small fraction of a coulomb of charge. A coulomb is a large number of electrons. A coulomb of charge would be that ginormous value of electrons. And just to give you a feel for that, if that much charge were to pass through your body in 1 second, you'd be dead, right? You'd be electrocuted. The amount of charge that I'm getting on this balloon when I rub it against my head is in the order probably of nanocoulombs, billionths of a coulomb, right? Very, very small in terms of coulombs, but actually still quite large in terms of electrons. So what Anna said is exactly right. When I rub this balloon against my head, what I'm doing is I'm pulling electrons off of my hair and putting them onto the balloon. So when I do that, if I'm pulling electrons off of my hair and putting them onto the balloon, what net charge is the balloon getting? Is that going to be positive or negative? Yeah, it's going to be negative because if I take something that's neutral and I add electrons to it, it acquires a negative charge. But then think about my hair. If I'm taking electrons off of my hair, if you start out with something that's neutral and you take electrons away, you're going to wind up with something that's going to be, you're going to have something that's positively charged. Mm-hmm. So to acquire a charge, a body either gains or loses electrons. Does it ever gain or lose protons? Let's go back to my helium picture. Would this helium atom ever gain or lose a proton? Kayla, you're shaking your head. Yeah, a couple of things we can say about it. You said that the nucleus determines what the atom will be, right? If helium did gain a proton, if it had 3 protons in the nucleus instead of 2, it would no longer be helium, right? It would be whatever has atomic number 3. And if you look it up, that's lithium. That'd be really weird if that happened. You know, suddenly it changes from helium to lithium. And it is possible to get it to do that, but it takes a lot of energy. It's not going to do that on its own. When you take 2 things and you bring them into close contact with each other, like you do when you take a balloon and rub it against your hair, the only thing that ever comes into contact from the atoms of the balloon and the atoms of my hair are the electrons. Because that's what's on the outside, right? So it's just electrons interacting with electrons. That's what gets exchanged. So we're never going to have to worry about protons getting exchanged. If that were to happen, that would be a nuclear kind of reaction, and we're not looking at that right now. Familiar with this term from chemistry? If you take a neutral atom and you give it a net charge, we call that an ion. So you can have a positively charged ion or you can have a negatively charged ion. So if we go back to this helium atom, and this helium atom grabs an electron from something else, so now it has 3 electrons and only 2 protons, then it would be a negative ion. A negative ion becomes negatively charged by gaining electrons. So in a negative ion, you're always going to have more electrons than protons. Right, what would that helium atom have to do to become a positive ion? Maureen, can you help me out there? What would have to happen to this helium atom to become a positive ion? Gain or lose what? Well, if it gains an electron, doesn't that give it more electrons than protons and make it negative? It would have to lose an electron. Yeah, the only way you can get a positive ion is if you lose an electron. And in doing that, the number of protons then is bigger than the number of electrons. Right, so it's only ever electrons that are exchanged. They're either gained or lost, and that determines whether it's positive or negative. All right, the next thing is how do we determine whether charges attract each other or repel? With those 2 pieces of tape, why in one case did the 2 pieces of tape go together, and the other case the 2 pieces of tape go apart? Right, this has to do with something called the law of electric charges. Anytime you have 2 bodies with a net charge, there's a force. There's an electrical force between them. But to figure out whether it's attractive or repulsive, you have to look at something and make a determination. And you know what it is?
It's kind of like magnetism. Opposite forces attract. So if one has a positive charge, it has less electrons. It needs more to what's one is negatively charged.
Right, so you said it's kind of like magnets. And how many of you ever played with magnets when you were little? Or if you ever did, if you have a North Pole, what kind of pole does the North Pole attract? Only attracts the South Pole. Remember that? Opposite poles attract, like poles repel. 2 norths would repel, 2 souths would repel. Charges behave the same way. Now please don't misunderstand me. Electrical charges are not the same thing as magnetic poles. Right? 2 different things, but they behave much the same way. In that like charges always repel each other, push apart. Opposite charges always attract. don't know if people work the same way or not. Probably not. We tend to be attracted more to people that are like ourselves. Although sometimes if you spend too much time with somebody who's exactly like yourself, it doesn't work out well either. Sometimes you start butting heads when that happens. But just to make sure you understand what we're talking about, here's the rule. You have a positive charge and a negative charge. The electrical force in those two charges is going to bring them together. Whereas if you have two positive charges, they're going to push apart. Likewise, if you have two negative charges, they're going to push apart. So in each case, you're going to have an electrostatic force, just a matter of what direction the force is. And eventually, we're going to learn how to calculate that force, too. That will come tomorrow. Some examples of this, let's go back to the tape again. Let me pull up the camera. The two pieces of tape. Let me try going a little bit closer to the camera this time. I'm not sure if that's going to work better or worse, but give it a try. Both pieces of tape are neutral. Right? When I take the one piece of tape and pull it away from the other piece of tape, what I actually did is I pulled electrons off of the one tape onto the other tape. So if I pulled electrons off of that tape would have acquired what kind of charge? Positive. And if I pull them off of that one onto this one would be negative. So if one's positive and one's negative, what do we expect them to do to each other? They should attract, and they sort of do. I think the fact that I got that crinkle in there kind of messed things up. Let me try it again. There we go, clearly attracting each other. Whereas, let me put that one down, that one was positive. Let's make another one that's positive by doing the same thing. Take a second piece of tape and make it positive. Put the negative one down and pull the other positive one off the table here where I sat it. Both of these are positively charged, and this time they clearly repel each other. And to give you some more examples of that, I want to have you turn your attention to the device there in the back of the room with the silver ball, which is called a Van de Graaff generator. So I want to zoom in on that. And if you move towards Reem a little bit, there you go, get you out of the line of fire there. And let's wait till we get a decent focus on that. This is called a Van de Graaff generator. You've probably seen them before at science museums and places like that, but it's used to demonstrate electrostatic charge. I'm going to get behind here and still in the line of the camera here. Okay. The way this works, if you look inside the tube here, there's a brown rubber band. It's essentially what it is, a big stretched out rubber band that's attached to an electric motor. And when I run the motor, it makes the rubber band start to move. And as that rubber band moves, as that big band moves, it causes electrons to take a trip from the bottom up towards the top, and they wind up being on top of this dome. So as the band rubs against, there's a felt roller down there at the bottom. As it rubs against that, it picks up electrons, takes them for a ride, deposits them up at the top. Now the metal dome starts out being electrically neutral, so when you add electrons to it, it's going to acquire a net, what kind of charge? Negative charge. We're adding electrons to it. Right? So here's the first question. Let me fire this thing up and run it for a little bit. Turn it this way. Run it for just a bit. I need to come over. There we go. Run it for just a bit. That should be good. Stop it. If I touch it like this, I get shocked. Maybe you heard that there. Why did I get shocked? What happened that caused me to get shocked? All right, what took place?
Negative charge, so it wouldn't give away some electrons.
Okay, electrons jump from there through the air onto my hand. Now my question is, why did they jump from there to my hand? Why didn't they want to stay there? Very simple. We had it on the board just a minute ago. Right, Mike? They're all repelling each other. They're like charges. Negative charges repel. In fact, before I touched them, would you expect that those electrons would have been all bunched together at one point in the dome? Now, if they repel each other, they'd be evenly distributed over the entire dome. But as soon as I give them a way to get further away from each other yet by getting close to it, remember, they're all pushing each other away. They push electrons through my body down to, guess where they end up? Down to the ground. Now, actually, a few of them may stay on my body. Let's try this. If I do that again, and walk over and I touch Kayla, she got a little shock along with that. So some of them were still on me, and they were repelled from me over to her. Now, this time we're going to do the same thing, but I'm not going to get shocked. And I'm hoping none of this fries the wireless electric mic that I'm wearing. We'll find out later if it does or not. But this time I'm going to run it, and I don't know how this is going to work, but Jenny, could you turn off one set of lights over there? That's good. I'm going to run it, and instead of me touching with my hand, I'm going to touch it with this sphere. As I do that, I'm not sure if that's showing up there or not. Try the other set of lights. Let's see if we can make it dark enough there. There we go. And again, I don't know if that's catching any of that or not. But what you're looking at there is miniature lightning. Now, lightning itself is not purple. It's more of a bluish color or whitish color. And electrons themselves, too, are not purple. I don't want you to get the idea that electrons are purple. What's happening is the electrons jump from the one ball to the other ball. They're energizing the air. As they energize the nitrogen in the air, the nitrogen gives off visible light. So that's what you're seeing. So you're seeing the result of the electrons passing through the air. A question I have for you is, where are the electrons going as I'm doing that? And Jenny, you want to get the lights back on? Are the electrons now on this ball? Now, I can touch that and I don't get shocked at all. I can touch that and really don't feel anything. So where'd they go? Will, any thoughts?
Through the wire, wherever that goes.
Okay, through the wire to right there to wherever that goes, right? Now, where does that go? That wire is connected to, on the plug, this middle prong. Now, anybody know what that middle prong in a plug is called? That's called the ground. Anybody know why it's called the ground? Now, right now, that's connected to, or just a minute ago, it was connected to this extension cord, connected to that. And if you follow that terminal of the extension cord back into the outlet, any guesses what it connects to? It connects physically to the ground. In other words, outside this school, there's a big old metal stake pounded into the ground somewhere, and that wire is connected to that metal stake. So think about those electrons that want to get far away from each other because they're pushing apart. As they push electrons further apart, they want to get as far apart as they can. Well, what better way to get further apart than get into the earth? Because once they get onto the earth, they get spread out over the entire surface of the earth. Right? So that's what was going on there. She mentioned this too. On a day like today, I can turn this thing on for a little bit, let it run, turn it off, come back to it a couple minutes later, and still get a pretty good shock, like I did just right there. And that's because today it's fairly dry. Had we tried to do this yesterday with the rain, it wouldn't have worked. I got it again. And that's because yesterday, those electrons would have had something else that they could have hopped onto besides me, namely the moisture in the air. Right? There's water vapor in the air. They're all trying to get away from each other. They can hop onto the water droplets in the air. But when the air is dry, there's no place for them to go, so they kind of hang out there until something comes along. And that's why, maybe you've noticed this before, maybe you haven't, but you're more likely to get a static electricity shock in the wintertime than the summertime because the air is so dry. And it's usually in the winter that when you're dragging your feet in the carpet that you get the shock. Let's try putting this on top of there. You have a little thing with a couple ribbons. And let me turn it on. And we'll let it run a bit. There, that little white guy's starting to go up. See him starting to jump up in the air a little bit there? As soon as I touch it, they go back down. Right, so explain the behavior of that. Why are they moving away from it when I don't touch it? As soon as I touch it, they go back down. What do you think's going on, Brett? Why would the white ribbons stand away from the ball?
Because it's trying to move further away.
Trying to move further away because we have electrons in the ball, we have electrons in the ribbons. Like charges repel, and that repulsion pushes it out. Even though you can't see electrons, you can see the effects of them being there or not, because as soon as I do that and remove them, everything goes right back down. And as another example of that, once you consider a stack of aluminum pie plates. Turn this thing on, we get electrons all over the plates. What are the plates going to do to each other? Like charges repel, and because of that, they repel with enough force to overcome the gravitational force that's holding them down. And eventually they all fly off the dome. And that brings up another interesting question. What would happen if you ran that thing while you were touching it? Any guesses as to what it would do if you put your hand on there the whole time while you were running it? Right, Taylor? All right, everybody always thinks your hair would stand up, but it turns out that if I didn't do something else first, my hair wouldn't stand up, right? In fact, I really wouldn't feel much at all. My hair wouldn't stand up, I wouldn't feel much at all, and that's because as the electrons would be produced, they would just be traveling right through my body, right down to the ground. And that's because my body really is an electrical conductor. Let's talk about a couple terms there, and then we'll come back and demonstrate some more things. The human body is a conductor of electricity. In other words, electrons can freely move throughout a conductor. A conductor of electricity is something that allows charged particles to freely move throughout it. And usually those particles are going to be electrons. Now, when you think of good conductors of electricity, what comes to mind? What kinds of materials? Probably think of metals. Yeah, all metals are good conductors of electricity. They're also good conductors of heat for the same reason. I don't know if in chemistry you remember talking about the different kinds of atomic bonds. Remember ionic, covalent, that kind of stuff? Hey, who are my AP Chem people in here? Yeah. There was another kind of bond called metallic bonds. Do you remember that? Right? Annie, you remember any characteristics of a metallic bond? Just remember that there was a metallic bond, right? In a metallic bond, here's the difference. In a metallic bond, the valence electrons really aren't tightly held by any one particular atom. It's kind of like communism, mutual sharing of all the assets. So the electrons they really don't feel a strong affinity for one particular atom, so they can very easily move throughout the crystal. Right? That's what makes conductors, metals, good conductors of electricity, because the electrons are free to move. But that's not why the human body is a decent conductor. You don't have a lot of metal in your body. But you know why? Yeah, and it's not so much water itself, right? Water is a pretty good non-conductor, right? It's what gets dissolved in the water. Salt and minerals, yeah, electrolytes. Again, let me take you back to chemistry for a minute. If you take an ionic compound, something like salt, and you dissolve it in water, right, here's our beaker. All right, we take some salt, sodium chloride, we dissolve it in water. What happens to that crystalline salt when it gets dissolved in water? Remember something called dissociation? He's like, huh? Remember you get sodium and chloride ions? Now, when sodium is in its ion form like that, is it bound up in a crystal unable to move? No, both of those ions are free to move throughout that liquid. So ionic solutions, another name for that is electrolytes. They're also very good conductors, like salt water, great conductor of electricity. Not because electrons can move throughout it freely, but because charged ions can move throughout it freely. That's why when you're at the beach and there's an electrical storm coming, the lifeguards are very quick at getting everybody off the beach. You ever notice that? They get excited when they see lightning. And that's because salt water, very good conductor of electricity. So the human body is a decent conductor of electricity because your blood has lots of dissolved ions in it. You're a good enough conductor of electricity to get you killed, right? If something's not a conductor, what is it? Opposite of a conductor is an insulator. Yeah, insulators are things where the electrons can't freely move through the material. When you think of insulators, you think of nonmetals. You know, things like plastic and rubber and paper, those are all very good insulators. Wood. And that's because in those materials, the electrons are very tightly bound by individual atoms. They can't move from atom to atom. It's more like capitalism now, right? I'm going to hang on to my assets. I'm not going to share them with you. There's a third class of materials that I want to just mention that's somewhere in between. You ever hear of semiconductors before? Semiconductors are used to make computer chips, things like silicon, germanium. But semiconductors, they have properties that are kind of in between. The electrons, you can get them to move, but only after you supply a certain threshold amount of energy. Well, the point is, the human body is a decent conductor, and because of that, yes, you can get shocked, but because of that, if we want to get your hair to stand up back here, what do we have to do to your body to get that to happen? Figure out which way to move there. If I just stick my hand on there, the charge is going to pass right through my body to ground. To keep that from happening, what do I have to do to my body? I have to stand up on something that's not a conductor, like this plastic stool. Right? This is an insulator, pretty good insulator. So if we, wrong way. If we stand on here with our hand on there, right, while it's running, right, then we can get the hair to stand up. And I should, Anna, can you angle that camera just slightly upward, because the way it is right now, we're not going to, there we go. And whoop, not that far up, not that far up. Back down a little bit, that's good. Maybe about right there. Now I just need to go over to where I'm on it, or whoever we get here to do this is on it. Close. And I need a volunteer. Okay, Jenny is going to volunteer. Come on over here. And you don't have any major metal jewelry on, do you? No, good. Okay, go ahead and put your hand right on top of there. That's good. We can see you real well. It's going to feel a little weird. It won't hurt, but it will feel a little weird. And it'll take a bit of time, but on the... It does feel weird. It does, yeah. And you can see the hairs in the front of her head are starting to stand up. Now take your head, just to get this started a little bit better, shake it back and forth a little bit. Yeah, that'll get things moving. There we go. Yeah, nice side view there. We can see it kind of standing out. And turn your head sideways, because now the back of your head, you can see it starting to stand out a good bit there. Now for longer hair, it takes more force to hold it up higher. But let me go ahead and turn this off. Take your hand off of there. Just take your hand off of there. Now watch this. Watch what happens when she touches my hand.
I hate getting shocked.
All right. Now, did you see her hair move down when she did that, though? As electrons left her, now step off of that, and everything should go back down. Let's see. Anybody else want to give this a... Will, you want to give it a try? Yeah. Come on in. Step up there. You're good. Okay, go ahead. Yep. Yeah, try shaking it a little bit. Yeah, now it's starting to... Okay, take your hand off there. I want to show you guys one quick thing while I have this set up before you leave. There's a box of... Oh, hang on a sec. Box of styrofoam packaging materials here. I want you just to see what happens if I put this on top of there and run it. Right, these things have very, very small mass, and because of that, the electrostatic forces are enough to do that. Right? It'll empty the box if you let it go longer. All right, pick it up there tomorrow.